Nice to meet you. I'm Prof.Joun, working for Gyeongsang in Korea. In this lecture, we are going to continue studying FEM of the one-dimensional steady-state heat conduction problem, conducting finite element analysis by hand calculation, following the same procedure with a standard FE program. For more detailed contents on this lecture, you can be advised by this reference. Hello everybody, I'm Prof.Joun. The entire lecture for variational approach to finite element method will be divided into three groups, that is, element equation, numerical integration, and finite element equations and solutions. This first lecture is aimed at formulating the element equation. Now let's follow the detailed procedure of finite element analysis of the same problem we have studied, using this simple finite element model composed of three elements with four nodes. This figure shows four linear interpolation functions defined at the nodes. The unknown function, that is trial function phi tilde, is a linear combination of these four interpolation functions. The coefficient pi I associated with the interpolation function ni is nodal value of the function. Directly differentiating the trial function pi tilde prime can be stated like this. Piecewise expression of interpolation functions are summarized here to help you understand them in more detail. You know, the problem we are solving has essential boundary conditions at both the ends of its given function values are all 0. The boundary conditions at both ends are thus formulated as pi 1 equals 0 and pi 4 equals 0, because nodal values at the left and right ends are pi 1 and pi 4 respectively. However, we won't plug this condition into the trial function at this moment. We will impose them on the finite element equations derived for the four nodal values just before solving finite element equations. Substituting this trial function into this functional, we obtain a new approximated function f tilde, which is a function of pi 1, phi 2, phi 3, and phi 4. It should be emphasized that the problem in the infinite dimensional function space was simplified to the problem in the four-dimensional vector space. After all, the variation principle changed to a nonlinear programming problem with two equality constraints like this. The necessary condition for the objective function f tilde to be extremum, that is partial differentiation with respect to pi I equals 0, gives us these four equations. I did not rearrange the equation on purpose to visualize the contribution of each element to the entire equation. For example, we can see all the terms contributed by the element 2 here and here written in blue color. Rearranging the equations in last slide, we obtain these assembled finite element equations before imposing the essential boundary conditions. The blue color means that the terms came from element 2. These assembled equations can be expressed in matrix form like this. Matrix K is called stiffness matrix and vector F is called force vector. Of course, this equation cannot be solved because of so-called Lenzweig motion occurring before the imposition of essential boundary condition on the assembled equations. When we express a set of equations separately only for an element, for example, these equations originated from element 2, we call it the element equation of element 2. I'd like to emphasize that these equations are meaningless before getting assembled in the entire finite element equations. That is, the solution of them are meaningless and they are prepared only to be assembled into this entire finite element equations. Following our special notation convention, the upper and lower bounds of integration, that is x3 and x2, are replaced by x2 and x1 for element 2 respectively. With a loss of generality, we attach its superscript 2 circled on the interpolation function and its derivatives, as can be seen in this matrix form equation, to designate their domain of definition. Phi 2 and phi 3 are replaced by phi 1 and phi 2 for element 2 respectively. It should be noted that this is just a general expression of element equation of element 2. Now we are going to map everything from global coordinate system to natural coordinate system using this mapping function. Plugging -1 for psi into the mapping function, we obtain x equals x1 for the element 2, implying that the left nodal point in global coordinate system is mapped to psi equals -1 in the local or natural coordinate system. Similarly, the right nodal point is mapped to psi equals 1. Plugging this mapping function into this and this interpolation functions defined over element 2, we obtain 1 minus psi over 2 and 1 plus psi over 2 respectively. We can thus conclude that these two functions of psi are interpolation functions in the natural coordinate system. The total differential dx can be calculated from the chain rule like this. A half length of line segment element is denoted by JE circled, called Jacobian of element 2. Now, left is to calculate the derivative of interpolated function with respect to x, that is global coordinate. Applying chain rule, we can express it as a function of psi, because the psi dx can be calculated from this mapping function, which equals 1 over Jacobian of element 2. Now everything is ready to be mapped. Plugging all mapped variables, functions, and terms into element equation for element 2, we obtain this final and general expression of element equation of element 2. Now we can see that everything related to the element 2 disappeared except the symbol for element 2, that is number 2 circled. In the previous slide, we derived element equation for element 2 in a step-by-step procedure. Now we can write directly the element equations for element 1 and element 3 by insight, as expressed here and here. For generalization, we can simply replace it by E circled. These equations are called element equations. Element equations are very important for programmers of FE programs. Of course, the element equation varies from problem to problem. With these element equations, they can develop the core routines of FE programs or software. Applying specific input values for each element, we can calculate all element equations in a systematic way, as stated here for element 1, element 2, and element 3. As already known, each set of linear equations are meaningless. They were prepared to be assembled. We better study how to calculate the definite integral in finite code before studying how to assemble these element equations.